guys, welcome back to chapter 16. In this video, we're going to talk about oxidation reduction reactions. So in the last video, we talked about assigning oxidation numbers or oxidation states to individual atoms. Now we're going to take that information and apply it to a chemical reaction. So what was the oxidation number as a reactant? What's the oxidation number as a product, and how did that change? Did it lose? Did it gain electrons? So to help us understand redox reactions, we have kind of fun little sayings that help us remember them. So first, the substance that loses electrons during a chemical reaction undergoes what we call an oxidation. So the substance that loses electrons is oxidized, or it's oxidation. The way that we remember that is Leo the lion says grr. So Leo, our lion, is named from loses electrons oxidation. So whatever loses electrons undergoes oxidation. The other side of this is a reduction. So reduction is the substance that gains electrons. So Leo, our lion, says grr gains electrons reduction or reduced. So that's how we remember who's oxidized, who's reduced, or who's undergone an oxidation, who's undergone an reduction. Monitor these changes. How do we monitor whether it loses electrons or gains electrons? Well, we assign the atoms oxidation numbers or oxidation states. So we would assign carbon in the reactant, carbon in the product with an oxidation number. And we look at, does that number go up? Does it go down? Or does it lose electrons? Does it gain electrons? Those two statements mean the same thing. So we're going to look at a redox equation, and we're going to identify where the reduction and where the oxidation takes place. So here's the chemical reaction that we're going to look at. So the first thing that we're going to do is we're going to kind of take inventory of the atoms that are present. And then we're going to look at what are their oxidation numbers or states on either side of the reaction arrow. One thing to point out here, oxygen appears in two different chemicals on the right-hand side. So we do have to treat those separately because the oxidation number in carbon dioxide may be different, it may be the same as the oxidation number in water. So we do have to treat those as two separate entities. So let's start with CH4 here, okay? So CH4, we're going to assign oxidation numbers. So oxidation of a free element, not a free element. Oxidation of a monoatomic ion, not a monoatomic ion. Some of the oxidation states, so when we add carbon and hydrogen together, it does have to be neutral. Metals, both of those are nonmetals. So we come over here to our hierarchy list. Fluorine not present, hydrogen. So the first element that we're going to assign an oxidation state for is hydrogen. And hydrogen is going to have an oxidation state of +1. Okay. Now that we have assigned the oxidation state for hydrogen, we're going to use that to deduce what the oxidation state is on carbon. So hydrogen is a +1, but there are 4 of them at the party. So altogether, hydrogen is going to bring a +4 to the table. Because we know that the sum of the oxidation states has to be 0, that tells us that the oxidation state on carbon must be a -4 to balance out that +4 from hydrogen. So carbon is a -4. All right, so now we're going to look at this oxygen O2 over here. So we're going to assign an oxidation state for oxygen. So when we go back to our hierarchy list, we start from this top. The oxidation state of a free atom is 0, and that is a free atom. So oxygen inherently exists as O2, so that means its oxidation state is 0. Why don't you guys go ahead and challenge yourself, see if you can pause the video and determine the oxidation states for the products. So looking at carbon dioxide, free element, neither one. Oxidation state of monoatomic ion, no. We know it has to be neutral. Neither one of those are metals, so we go to our nonmetals. Not fluorine, not hydrogen, oxygen. So oxygen is going to be the first atom that we give an oxidation number to for this compound. So the oxidation number for for oxygen is a -2. Now, oxygen is a -2. There are 2 of them at the party, so altogether that's a -4. So what must the oxidation number be on carbon to balance that out? Well, it's got to be a +4 in this case. Moving on to water, again, not a free element, not a monoatomic ion. We know it has to be neutral. No metals, nonmetals. So we go to our list. H2O, so no fluorine, hydrogen. That's going to be the first one that we assign an oxidation number to. So hydrogen is going to be a +1. And we see that there are 2 hydrogens at the party. So hydrogen brings a +4 to the table. Nope, just kidding. It's a +1. There are 2 hydrogens. So hydrogen brings a +2 to the table. So what must this one oxygen be to balance out that +2? Well, it's got to be a -2. So in this case, both oxygens had the same oxidation number or state. Might not always be the case, so we do have to treat them separately. Right, so now that we have assigned oxidation states or oxidation numbers, we can take a look at how things changed or how things stayed the same to identify oxidation and reduction. So the first thing I see is that the carbon did change, right? So carbon went from a -4 to a +4. Now we're in the backwards world of electrons, right? So electrons are negatively charged particles. So when the carbon had a -4 oxidation state and then went to 0 and then went to a +4, that tells me that it lost those negatively charged particles. So this was the one that lost electrons. Okay. Remember our little acronym, Leo the lion says GR. So lose electrons, oxidized. This is the one that undergoes oxidation. Lost electrons, and that was the oxidation. That means there must be a reduction somewhere. There must be somebody gaining electrons. If I look at hydrogen, so hydrogen started with an oxidation number of +1 and ended with an oxidation number of +1. He didn't change. He didn't lose or gain. He just stayed the same. Now, if we look at oxygen, he went from a 0 to a -2. So something happened with oxygen for sure. Okay. So how do we go from a 0 to a -2? Oxygen took on or gained those negatively charged particles, those negative electrons. So oxygen gained electrons, and that means that is our reduction. So in our acronym, Leo the lion says GR, gain electrons reduced. I know this idea of gaining negatively charged particles, losing negatively charged particles is difficult. It's like a backwards world. So here's something else that's really helped me with identifying oxidation reduction. I always know there can't be one without the other. So if I can identify reduction quickly, I know the other change must be the oxidation. So another way that I recognize reductions is the oxidation number gets reduced. So oxidation number gets reduced or it goes down. So when we went from a 0 to a -2, that number was reduced or it went down. That's where the reduction takes place. When we went from -4 to +4, that number went up. So that is not a reduction. That's the other one. So when that number is reduced, that's my reduction, gain electrons reduced. Then I know the other one must be the oxidation. So this is a skill that you're going to need to have as we proceed through this chapter. So please make sure you guys are practicing redox reactions before we make it more complicated and start balancing reactions. I hope you found this helpful.